Hello and welcome to this video on confidence intervals. In this video, we will be doing 4 different things. First of all, we'll talk about the basics of confidence intervals. Second, we'll play the game We Never Do This. Number 3, we will actually practice with an example using numbers and graphing that out. And then finally, at the end, we will kind of summarize 4 truths that kind of surround this idea of confidence intervals. So for starters, let's talk about the basics of confidence intervals. The first thing to remember is that there are two methods of statistical inference. And so if we start off with a population and we draw a sample from that population, remember we want this to be a random sample. That gives us an element of chance. That sample is what we use to measure something. So we measure different variables and we calculate statistics about those variables such as x bar, standard deviation, that kind of thing. And then based on those things that we measured from our sample, we infer back to the population. So we have sample statistics that infer population parameters. And if we were to use the average, the population parameter then would be mean. And there are 2 different ways of inferring. One is hypothesis testing. The other is called estimation. And so that's what we're going to be doing today, is estimation. And what we're estimating today is we're estimating mu from x bar. So that's where we're estimating our population parameter from our sample statistic. So if we were to graph this out, we would talk about a 95% confidence interval for mu is equal to x bar plus or minus 2 standard errors. Now we've seen standard errors before, and they are calculated exactly the same for this particular method of inference as we did for hypothesis testing. Specifically, let's give ourselves an example where we have a population standard deviation, or sigma, is equal to 40. Our sample size is equal to 64. Therefore, our standard error is equal to 40 divided by the square root of 64, or 5. So it's the sigma over the square root of n. So that's not a new calculation. And basically this 95% confidence interval of mu really tells us our success in capturing the parameter that it seeks. So here we're trying to capture mu. So this is success in this 95% in capturing the parameter it seeks. So hence the hide and seek. Hide is the parameter, or in this case mu. And we are going looking for it by doing this confidence interval activity. And 95% of the time, we will be successful. We like to be successful as much as possible. But what that also means is that 5% of the time, we will not succeed in capturing mu. And so that's what confidence intervals are all about. So let's go on to talk about this game, We Never Do This. Right now, you have probably started becoming really excited about playing this game, We Never Do This, because you knew it was coming up. And so when we sample a population, we generally take a sample, not 100 samples, but we're gonna pretend that we take 100 samples, and each of those samples has a different x bar, or sample mean. We build a 95% confidence interval around each of those just by doing that. This is how we do it. We take x bar plus or minus 2 standard errors, and then 95 of those 100 will include the mean, 5 of them will not include the sample or the population mean. So what this tells us is that 95% of the time we will be successful in capturing the parameter, the population mean, in our 95% confidence interval. And the other 5% of the time, unfortunately, we will not be successful. So let's build this confidence interval, x bar plus or minus 2 standard errors. And so here's our example over here on the right-hand side. And what we're told is that x bar is equal to 185. So the point estimate for mu is equal to x bar. And so I'm going to put that down here in our 95% confidence interval, 185. Remember, this is kind of a long continuum. Here we have 185. And then if we were to take plus or minus, in other words, above and below that 185, 2 standard errors. And if I take my 2 times my standard error of 5, so plus 2 standard errors, I'm going to do this in green, plus 2 SE is going to be 2 times 5 is 10. So 185 plus 10 is 195. And then minus 2 standard errors, or minus 2 times 5, is going to be minus 10. So this is going to be 175. So my 95% confidence interval is anywhere between 175 and 185. And I could draw that like this. Here's my point estimate. I go up by 2 standard errors and down by 2 standard errors. And so there's my confidence interval around that point estimate. Now remember, we're estimating mu. And what we know is if we did that 100 times, we would get a whole bunch of different x bars. They wouldn't all be 185. Just by this random chance, we're going to draw a sample that has a sample mean of something else. Let's say that we draw a sample with a sample mean that's lower, and we build a confidence interval around that one, and so on. So we would have a whole bunch of these x bars if we did this 100 times. Now we're not going to. We're just going to use this one example for our confidence intervals activity. So I'm going to erase that just so it's not in our way later. So here we have our point estimate, our 95% confidence interval. And this interval, I'm going to go ahead and write this. This interval will capture or find, it will find the mu, the population mean, 95% of the time. So 95% of the time, our sample confidence interval will capture the population mean. Now, we don't know if our one sample, remember, we just take one sample. We just take a sample here. We don't know if ours is one of those or not. Our sample actually does or does not, but 95% of them, if we were to do this multiple times, then it would capture that. Okay, so let's talk about what that means then in terms of some specific hypotheses. So I'm going to write my hypotheses here. Let's say I have a null hypothesis that mu is equal to 170. We've seen this one before. These are weights. The alternate then would be that mu is not equal to 170. So we're doing a two-tailed test, and we're going to stick with that pretty much for the remainder of the course. So we're going to test whether the average is equal to 170. Well, if I graph 170 here on my 170, what I notice is that that does not fall within my 95% confidence interval. And so what we conclude then, based on what we've done so far, is that we are 95% sure that our population mean should be somewhere between 175 and 195. Well, since this 170 falls outside of that range, we would reject the null. We would say, nope, I don't think that's true. I think that the mu is something that's not equal to 170. Let's do a second example. Let's say we test a null hypothesis that the average is equal to 176. My alternate is that the average is not equal to 176. So let's graph that here, and that would put our 176 right here. And what you'll notice is that that does fall within the 95% confidence interval. And so what we say is fail to reject the null. I don't have enough evidence to say that that's not true. Now, technically, if you just were doing algebra, would you say that 176 equals 185? There's no algebra equation that will get you to there. But what we're wondering is not whether it's different, is whether it is statistically significantly different from 176, this difference between 176 and 185. Is that statistically significantly different? Because remember, we're just making an inference about this particular scenario. Let's do a third one, and we'll test whether the population mean, whether it's realistic if our population mean equals 187. Now I'm getting even closer here to my point estimate of mu. So here's 187, and so we're just a little tiny bit of a difference away. And so because that falls within this 95% confidence interval, 175 to 195, the alternate here would be the mu is not equal to 187. We go ahead and say, fail to reject the null. I don't have enough evidence to say that that's not true. When it was 170, I did have pretty good evidence. This is only going to happen 5% of the time for it to be farther than 2 standard errors away from what I'm saying is my, my sample mean. So that kind of gives you a clue into what we do with hypothesis testing and how hypothesis testing relates to this confidence interval that we have built around the sample mean. Now, what happens when our sample size goes up? And I want to do an example with you because I think this is important. Remember, we have a sample size, and that sample size influences so many different things. It's really important to think about the sample size when you're thinking about all of these different scenarios. So here we have sigma. That stays the same. Sigma is 40. Our new sample size, I'm going to take 64 and I'm going to multiply it times 4. And you'll see in a minute why I do that. So let's say my sample size is equal to 256. So instead of drawing a sample of 64, I say, you know what? I'm going to get more people. I'm going to really understand this. The more I have, the more I can be sure of this 95% confidence interval that I have. So my new standard error is equal to sigma over the square root of n. So that's equal to 40 divided by the square root of 256, which is equal to 2.5. Go ahead and do the math because it's helpful to really get that in your brain. And what you'll notice happens when I multiply the sample times 4, my standard error gets cut in half. And that is always true. As long as your sigma stays the same, if I divide by the square root of something that's 4 times bigger, it's going to make the end product be half as big. So if I multiply this number times 4, I would end up with a standard error equal to 1.25, and I could keep doing that. So the larger and larger and larger the sample, the narrower and narrower and narrower the confidence interval. So if I do this same exact example where I have point estimate is equal to 185 plus or minus plus 2 standard errors and minus 2 standard errors around that, what I will end up with is 2.5 times 2 is equal to 5. So that's this right here. That's this plus and minus 2 standard errors. So plus 2 standard errors is equal to 190, and minus 2 standard errors is equal to 180. And what you'll notice is that not only did the standard error get cut in half, but now my 95% confidence interval got cut in half too. So increasing the sample size by a factor of 4 makes your 95% confidence interval drop by 2. An important thing to remember is that this 2 is really just an approximation. In real life, it is 1.96. It's just harder to do the math and have all these numbers with decimal points. So I use 2 in all of my examples. In the real world, you would have to multiply that by 1.96. So this would be a teensy bit narrower than 180 to 190. But again, this interval will, for a sample size of n equals 256, will capture the population mean 95% of the time. So 95% of the time, my population mean will fall within whatever my sample is. And let's draw this new one. So here's my point estimate, plus or minus 2 standard errors. With a larger sample, see how my 95% confidence interval shrinks? So that's an important relationship with sample size. So as n goes up, the confidence interval gets narrower. Now, the 4 truths to end our video. One thing that I want you to notice is that the confidence interval extends equally above and below the x-bar, or our sample mean. Sometimes you will get test questions where you have, say, a sample mean of 185, and they ask you, what's the most likely confidence interval? Well, I can tell you for sure that the confidence interval will not be 170 to 175, because 185 isn't even in there. And our sample mean has to be in the middle of the confidence interval. So pay attention to that. The next thing is that if our 95% confidence interval includes the null, and that was the case here with the 176 and 187, then we fail to reject the null, and that's exactly what we did. We said, yeah, that seems pretty reasonable. We could go with those 2 scenarios. Another way of saying that, these are all equivalent. Another way of saying that is this was not statistically significant. Another way of saying that is that the p-value would be greater than or equal to 0.05. So if the p-value is greater than 0.05, it's not statistically significant, we fail to reject the null, and the 95% confidence interval will include the null value, that mu equals to 176 or mu equals to 187. An interesting thing happened, and I just want to point this out, an interesting thing happened when our confidence interval got narrower here. Notice that this 176 no longer falls between 180 and 190. So we gained the ability to say that 176 is too far away from 185. And so in that case, what we would do, if we were using this particular scenario with an n of 256, we would say, yes, I do have adequate information to reject that null, and I would say my mean is not equal to 176. So that kind of goes along with what we're learning right here. So this is dependent on n. As n increases, my confidence interval decreases, and I might change my interpretation of what that means. So on the flip side of this one, if my 95% interval does not include the null hypothesis, and that was the case here for 170, then I reject the null hypothesis. I say that there is a statistically significant difference, and my p-value is going to be less than 0.05. Those things always go together. Very rarely in the world do we say always. But if I reject the null, I'm not going to say, oh, that's not statistically significant. If we're talking about a 95% confidence interval, then my p-value of 0.05 on both of these cases, 95% confidence interval, is going to be either less than 0.05 or greater than 0.05. So this 95 and this 5 are the complements of each other. If we were to do something where we change this to a 99% confidence interval, then my p-value I would know is going to be greater than 0.01 because 99 is the complement of 1. Those numbers, the 0.95 and the 0.05 adds up to 100, or the 95 and the 5, or the 99 and the 1 adds up to 100. So these are the kinds of things that you'll need to know how to manipulate. And what will happen on a kind of like a testing scenario is that they will give you a 95% confidence interval. And then they'll ask you, do you fail to reject the null? Or is that statistically significant? Or what is the most reasonable p-value that goes along with that 95% confidence interval? Or they'll give you a p-value and then they'll ask you, what do you think is the 95% confidence interval for that particular statistical test? They might say a test was run and it was not statistically significant. What do you think is the 95% confidence interval for that null hypothesis? So being able to manipulate yourself back and forth across this if-then is going to be, both directions is going to be very crucial. So that concludes our video on confidence intervals. Thank you for joining me.